Hello everyone, welcome back. I am Dr. Geraldina Fernandez, Assistant Professor, Department of Science from the Bhopal School of Social Sciences. Students, in the last session, we have studied the definition of calculus, definition of differentiation, main rules of differentiation, and some applications of derivatives. So now, in today's session, we will be talking about the chain rule of differentiation and differentiation of implicit functions. So without any further ado, let's start today's session. So the very first topic of today's session is chain rule of differentiation. But before explaining the rule, I would like to cite an example. Like, have you ever received any present from someone where when you open the first box, there is a second box. When you open the second box, there is a third box. When you open the third box, there is a fourth box, and so on and so forth. So you keep opening the boxes until you reach the tiny box that has the present for you. So chain rule is very similar to this. You keep on differentiating it in a chain so that you reach the derivative of the standard function. So let's understand this with the help of some examples. So the first question is, find dy over dx if y is equal to x cube plus 2x whole square. So in this example, we are having function of function. So differentiating both sides with respect to x, we will get dy over dx equal to d by dx of x cube plus 2x whole square. Now using the first formula of differentiation, that is d by dx of x raised to the power n is equal to n times of x raised to the power n minus 1. So applying the formula, comparing both the powers, we will get n is equal to 2. So dy by dx is equal to 2 into x cube plus 2x raised to the power 2 minus 1. We have applied this formula. And since we are having function of function, so we will have to apply chain rule, and that is we will multiply d by dx of x cube plus 2x. Now 2 into x cube plus 2x raised to the power 2 minus 1 will give you 1, multiplied by, here we will apply the rule of differentiation, that is the derivative of sum of two functions is equal to the sum of the derivatives of the two function. So here that would become d by dx of x cube plus d by dx of 2x. Now this thing will be written as it is, 2 times of x cube plus 2x into, here we will apply the same formula, n is 3, so that will become 3 times of x raised to the power 3 minus 1 plus, here we will apply one more rule of differentiation, that is the derivative of the product of a constant and a function is equal to the product of the constant and the derivative of the function. So differentiating x with respect to x will give you 1. Here we will get 1. So the final value of dy by dx is 2 into x cube plus 2x multiplied by 3x square plus 2. So this is the value of the derivative of the function when the original function was y equal to x cube plus 2x whole square. Find dy by dx if y is equals to e raised to the power square root of 1 plus x square. So in this particular example, we are having function of function, that is composite function. Here we are having exponential function, and within that exponential function we are having algebraic function. So we will write the given function y is equal to e raised to the power square root of 1 plus x square. Now we will differentiate both sides with respect to x. So dy by dx is equal to d by dx of e raised to the power square root of 1 plus x square. Now we will assume the power as a single function of x. We will assume it as x and use this formula of exponential function. Dx of e raised to the power x is equals to e raised to the power x. So in the similar manner, we will get dy by dx. Applying the same formula, we will get e raised to the power square root of 1 plus x square multiplied by chain rule of the power, that is d by dx of square root of 1 plus x square. Now using the formula of d by dx of x raised to the power n, here the value of n is 1 by 2, this is square root, so the value of n is 1 by 2. So the result will be 1 by 2 into 1 plus x square raised to the power 1 by 2 minus 1 into, we have to differentiate till we get the derivative of the standard function. So d by dx of 1 plus x square. Exponential function will remain as it is, multiplied by 1 by 2 into 1 plus x square raised to the power minus 1 by 2. Here we have taken the LCM of the power, that is minus 1 by 2, multiplied by, here we will use the derivative of sum of two functions. The rule of derivative of sum of two functions is equal to the derivative of the first function plus the derivative of the second function, and that is equal to e square root of 1 plus x square multiplied by 1 by 2 into 1 plus x square raised to the power minus 1 by 2. Now as we all know that the derivative of a constant is always 0. So derivative of 1, that is d by dx of 1 is 0, plus the differentiation of x square will give you 2x. Now on simplifying, we will get 0 plus 2x will give you 0 plus 2x will give you 2x. Now this 2 is coming in the numerator as well as in the denominator, so that will get cancelled. So finally we are getting dy by dx is equal to x into e raised to the power square root of 1 plus x square multiplied by 1 plus x square raised to the power minus 1 by 2 was here. So we will shift the negative sign to the denominator and we will get square root of 1 plus x square. So dy by dx is equal to x into e raised to the power square root of 1 plus x square divided by square root of 1 plus x square is the final value of the derivative of the function where y was equal to e raised to the power square root of 1 plus x square. Now the third question is, find dy by dx if y is equals to x raised to the power x. So here we are having y is equals to x raised to the power x. Now this example is of the form y is equals to u raised to the power v, where u and v both are functions of x. So in this case, when you are having function raised to the power function, it is convenient to take log on both the sides and then differentiate. So doing the same procedure, we are marking this as equation number 1 and then taking log on both the sides. Why we are taking log? Because the example is of the form y is equals to u raised to the power v, function raised to the power function, and where u and v are functions of x. So taking log on both the sides. Now before differentiating, we will apply the property of log, that is log n raised to the power m. So that is equal to m into log n. So here applying the property of log, log x raised to the power x, by this property can be written as x log x. Now differentiating both sides with respect to x. Now when you differentiate log y, please remember that y is a function of x. So log differentiation of log y will give you 1 upon y into chain rule, that is dy by dx. Don't forget y is a function of x. So when you differentiate log y, we will get 1 by y into dy by dx is equal to, now differentiating the right hand side, here we are having product of two functions, that is an algebraic function and an logarithmic function. So assuming the first one as the first function and this log as the second function. So we will have to apply the product rule of differentiation, that is the first function is written as it is multiplied by the differentiation of second. So differentiation of log x is 1 by x plus the second function is kept as it is multiplied by the differentiation of first. So differentiation of x is 1. So 1 by y d by dx is equal to, here we get x gets cancelled and we are getting 1 plus log x. So the final value of dy by dx is, you will have to multiply the whole equation by y. So, we will get dy by dx is equal to y into 1 plus log x. Now, the value of dy by dx should be in terms of x. So, from equation number 1, we can replace y by x raised to the power x. So, the final value of the derivative is dy by dx is equal to, we will replace this y by x raised to the power x from equation number 1 into 1 plus log x. So, this is the final value of dy by dx when the original function was y is equals to x raised to the power x. So, next topic of today's session is differentiation of implicit functions. So far, we have differentiated functions in which one variable was expressed entirely in terms of another variable. Now, let's check out these two examples. Y is equal to x square minus 3x plus 2. Here, y, which is the dependent variable, is expressed entirely in terms of the independent variable x. We have done the differentiation of such functions. Now, the second example is x cube minus xy plus y square is equals to 4. In the similar pattern, we will try to find the value of y. So, from the second and third term, we will take y as common. So, we will get x cube minus of, I am taking minus y as common. So, we will get x minus y is equals to 4. Now, I want to find the value of y. So, that means I will shift this plus x cube to the other side. So, that will become minus y into x minus y is equals to 4 minus x cube. Now, dividing the whole equation by minus of x minus y. So, what we will get? We will get y is equal to 4 minus x cube divided by minus of x minus y. Now, multiplying this negative sign within the bracket, we will get y is equal to 4 minus x cube divided by, multiplying this negative sign within the bracket, we will get y minus x. So, in this example, y cannot be expressed entirely in terms of one variable. Here what we are getting? We are getting y in terms of x and y. So, such functions in which one variable cannot be expressed entirely in terms of the another variable is called as the implicit function. So, from here we have got the definition of implicit functions. What are implicit functions? Those functions in which one variable cannot be expressed in terms of the another variable or vice versa. So, this is an example of implicit functions. Now, what are those functions? The first example, here y was expressed entirely in terms of x. So, this function is called as explicit function. Now, so far we were differentiating explicit functions. Next, our aim is to differentiate implicit functions. So, the question is how to differentiate implicit functions? Well, for that, leave the whole equation as it is and differentiate both sides with respect to x. So, let us understand implicit functions and differentiation of implicit functions with the help of few examples. So, the question is find dy by dx if x cube minus xy plus y square is equals to 4. So, this is an implicit function and we want to differentiate it. So, differentiating both sides with respect to x, we will get d by dx of x cube minus xy plus y square is equal to d by dx of 4. So, here we will use the rule of differentiation, for sum of functions. So, the derivative of sum of functions is equal to the sum of the derivative of the function. So, here that would become d by dx of x cube minus d by dx of xy plus d by dx of y square is equal to differentiation of a constant is 0. Now, here we will use the formula d by dx of x raised to the power n, and that is equal to n times of x raised to the power n minus 1. So, x cube will become, differentiation of x cube will become 3 x raised to the power 3 minus 1 minus of, now here we will use the product rule. Since we are having x into y, that means we will have to choose one as the first function and the remaining one as the second function. So, I am assuming x as the first function and differentiating it with respect to x. So, first function is x multiplied by differentiation of second. So, differentiation of dy y will give you dy by dx plus the second function is kept as it is and we differentiate x with respect to x will give you 1. So, this is the product rule plus differentiation of y square will give you 2y times of dy by dx and that is equal to 0. So, 3x square minus, in the next step we will multiply the negative sign within the bracket. So, we will get minus of x dy by dx minus of y plus 2y dy by dx is equals to 0. Now, from the second term and the fourth term we will take minus of dy by dx as common. So, what we will get? We will get 3x square minus dy by dx into x minus 2y minus y is equal to 0. So, now we want to find the value of dy by dx. So, for that we will shift 3x square and y to the other side. So, we will get minus of x minus 2y into dy by dx is equal to y minus 3x square. Now, dividing the whole equation by minus of x minus 2y. So, we will get dy by dx is equal to minus of y minus 3x square divided by x minus 2y. So, this is the final value of the derivative when y was expressed in terms of the implicit function. Next question is find dy by dx if x cube plus y cube is equals to 3y. So, this is an implicit function. We will differentiate both sides with respect to x. So, we will get d by dx of x cube plus y cube is equal to d by dx of 3y. Now, here we will use the rule of differentiation. The differentiation of sum of two functions is equal to sum of the differentiation of the first function and the differentiation of the second function. So, d by dx of x cube plus y cube will give us d by dx of x cube plus d by dx of y cube is equal to d by dx of product of a constant and the function is equal to the product of the constant and the derivative of the function. So, this is another rule. Now, applying the formula of differentiation, that is d by dx of x raised to the power n is equal to n times of x raised to the power n minus 1. So, here we will apply the formula of this differentiation. X cube will give you 3x square plus differentiation of y cube. Please remember that y is a function of x. So, differentiation of y cube will give you 3y square into dy by dx. You will have to apply the chain rule is equal to 3 dy by dx. Now, after this we will shift the terms that contain dy by dx to one side and those terms which does not contain dy by dx to the other side. So, we will shift this 3x square to the other side. So, that becomes 3y square dy by dx minus of 3 dy by dx is equal to minus 3x square. So, from here we can take 3 dy by dx common from the left hand side. So, we will get 3 dy by dx into y square minus 1 is equal to minus 3x square. Now, we can see we are having 3 on both the sides. So, this gets cancelled and we get the value of dy by dx as minus x square upon y square minus 1. So, this is the final value of the derivative of the function when the function was in form of implicit. I hope this session was fruitful for you. Thanks for watching. Thank you.